This is Dr. V.C. Sontake, Assistant Professor in the Department of Mechanical Engineering, and I am going to take the course Heat Transfer. Objectives of this video lecture are: number one, to discuss and explain various aspects of lumped parameter analysis. Number two, to define thermal time constant and its significance with regard to the transient heat conduction. Objective number three is to define Fourier and Biot numbers and their significance in transient heat conduction process. And last objective is to explain to apply lumped parameter analysis based on its selection criterion. So let us start discussing some of the important points of the lumped parameter analysis. It is also called as lumped capacitance analysis. Now, as we have already discussed, when a body whose surface area is very large as compared to its volume and having thermal conductivity value infinite, and when this body undergoes heating or cooling as a result of very large surface area and very large thermal conductivity value, the body does not offer any internal conductance resistance to the path of the heat flow. And because of this negligible or zero internal conductance resistance, there is no temperature gradient within the body. The temperatures of the various parts of the body are assumed to be constant at a particular instant of time. So when such body whose surface area is very large and thermal conductivity value is infinite undergoes heating and cooling without offering any internal conductance resistance and its temperature is uniform with respect to time, is called as Newtonian heating and cooling. And lumped parameter analysis is used to calculate the variation of the temperature of the body with respect to the time. Here the meaning of lump is the temperature of the body is assumed to be constant at all points at a particular moment of time. And to analyze the lump system, the lumped parameter analysis is used. The following equation is used to calculate the temperature of the body after any interval of time tau from lumped parameter analysis. T minus T infinity over Ti minus T infinity is equal to e raised minus HAS over rho VCP into tau. This equation can also be written in this fashion: T minus T infinity over Ti minus T infinity is equal to exponential of HAS over rho VCP into tau. Now, based upon these two equations 1 and 2, let us understand some of the important aspects of this lumped parameter analysis. So, aspect number 1, from equation 1 and 2 and from this figure U 2.1 for Newtonian heating or cooling, it is clear that temperature of the body changes exponentially in transient heat conduction, and the rate of change of the temperature depends upon the parameter HAS over rho VC. Equation 1 and 2 and figure U 2.1 also indicate that temperature of the body or it takes infinite time to reach the temperature of the body equal to the temperature of the surrounding environment and to attain a steady state condition thereafter. However, as you can also see here, the difference between T and T infinity of the body and surrounding respectively becomes extremely small after a very short period of time, and beyond that period of time temperature of the body almost becomes equal to the temperature of the surrounding. For example, in case of heating, as you can see here, this will, in case of heating, T infinity will be the surrounding temperature, which will be higher than the temperature of the body. So temperature of the body is changing exponentially, and after a short period of time the difference between T and T infinity will become equal, become very small, and thereafter the temperature of the body will almost equal to the temperature of the surrounding. In the similar way you can explain for cooling as well. For cooling, this will be the environment temperature. T infinity will be less than the temperature of the body. So temperature of the body will change exponentially, and after certain period of time the difference between T and T infinity will become very small, and temperature of the body will be almost equal to the surrounding temperature. Following figure U2.2 shows the change in temperature of a body with respect to time, both for heating and cooling. So this is the plot between non-dimensional temperature distribution parameter T minus T infinity over Ti minus T infinity and time tau. So as you can see here, for a particular value of the parameter HAS over rho v Cp, with the increase of time, the value of this non-dimensional temperature distribution parameter increases. That means with the increase of the time, body temperature reaches equal to the temperature of the surrounding. Similarly, for a particular at a particular moment of time, for a particular moment of time, increase in the value of HAS over rho v Cp increases the value of T minus T infinity over Ti minus T infinity. So with the increase of the parameter HAS over rho v Cp, body will approach to the temperature of the surrounding very fastly. In the similar way, for cooling, for a particular value of HAS over rho v Cp, temperature of the body reaches equal to the temperature of the surrounding as the time increases. And at a particular moment of time, as the value of HAS over rho v Cp decreases, body reaches to the temperature of the surrounding very fast. So this way you can interpret the effect of the parameter HAS over rho v Cp on the variation of temperature of the body with respect to its surrounding temperature. Observation number 2, or important point related to lumped parameter analysis. Now we have this quantity rho v Cp over HAS, where rho is having the unit of density, V is volume, H is the unit of watt per meter square Kelvin. So joule per second will be watt per meter square Kelvin, and AS is the surface area having unit meter square, and finally unit of Cp is joule per kg Kelvin. If I simplify all these units, I will get the unit of this parameter rho v Cp over HAS as second. So the parameter rho v Cp over HAS has the dimensions of time, and this parameter is called as time constant and is denoted by tau suffix th. Now what is its significance? The thermal time constant indicates the rate of response of a body or system to sudden change in temperature of its surrounding. That is, it indicates how fast the body will respond to the change in the environment or surrounding temperature. For example, let's say a body is at 100 degrees Celsius and it is exposed to the environment at 25 degrees Celsius. For a particular case, let's say thermal time constant value is 100 degrees Celsius, 100 seconds. What does it mean? The body will take 100-second time to reach the temperature of surrounding of 25 degrees Celsius. And if the thermal time constant value is 5 seconds, body will take 5 seconds to reach from the temperature of 100 degrees Celsius to 25 degrees. So if thermal time constant value is high, body will respond slowly to the change in the temperature of surrounding, and if thermal time constant value is small, body will react or respond rapidly to sudden change in the temperature of the surrounding. Now thermal time constant can be given as rho v Cp upon HAS. In this, 1 upon HAS can be represented by RTH and rho v Cp can be represented by DTH, where RTH is resistance to convective heat transfer denoted by 1 over HAS, and CTH is lumped thermal capacitance of solid denoted by rho v Cp. So it is clear from this relationship, if you increase the value of RTH or CTH, it will also increase the value of thermal time constant. So increase in the thermal time constant will make a body or solid to respond slowly to any change in its surrounding temperature, and it will increase the time required by the body to reach the thermal equilibrium with its surrounding. So from figure U2.3 it is very clear. If the value of rho v Cp by HAS is less, it is lesser value for this yellow line. So body will take a small time to reach to the temperature of the surrounding, if it is the case of cooling. And if the value of thermal time constant rho v C over HAS is very high, this is for this gray line. In this case, body will take longer time to reach to the equilibrium with its surrounding. That is, it will take more time to reach the temperature of the surrounding. So that is the significance of thermal time constant. For example, thermocouple. Thermocouples are used to measure the temperature of any body, and it is expected that thermal time constant value for thermocouple should be as minimum as possible. The ideal condition must be 0. What does it mean? Let's say I want to measure the temperature of the body at 10 degrees Celsius. So we have to touch one of the end of the thermocouple with that body. So what it is expected from thermocouple? It should reach to the temperature of the body without no delay. That is the temperature of 10 degrees Celsius. So minimum will minimum will be the thermal time constant for thermocouple. More rapidly it will reach to the temperature of the body whose temperature is to be measured. Or you can also say it will reach very rapidly to the equilibrium, thermal equilibrium condition with the body whose temperature is to be measured by thermocouple. Observation number 3, figure 2.4 shows an analogous electrical net circuit for a lumped heat capacity system which is undergoing transient heat conduction process. In this equation, Cth is equal to rho v Cp is equal to thermal capacity of the system. The value of this Cth can be obtained from applying the similarity between thermal equation of heat transfer amount in joule is equal to rho v Cp into T is equal to Cth into small t, where small t is the temperature of the body at any moment of time, and corresponding electrical equation is small s is equal to C into E, where the small s denotes capacitor charge in corresponding electrical circuit, capital C is the capacitance of the conductor, and capital E is the voltage. So when you close the switch S in the figure U2.4, the solid is charged to the temperature theta, where theta is the excess temperature, can also be given by expression T minus T infinity, where T is the temperature of the body. But when we close the switch, the thermal energy stored as Cth in the body is dissipated because of resistive forces through the thermal resistance Rth, and the temperature of the body decays with time. So from the above analogy, it can be recommended that RC electrical circuit is used to determine the transient behavior of the thermal system. If you want to design an electrical circuit, we have to take into consideration RC circuit to find out the transient behavior of any system. Point number 4. Now the lumped parameter equation in slide 1. This equation was appeared T minus T infinity over Ti minus T infinity is equal to exponential of HAS over rho VCP into tau. Now in this equation 1, the term HAS over rho VCP into tau can be rearranged in non-dimensional form as follows. So HAS over rho VCP into tau can be written as H into V over K into AS, where V is the volume of the body and AS is the surface area, into AS square K over rho V square into Cp into tau. Let me correct this term. So HAS over rho V Cp into tau can also be written as HV over K into S, where V is the volume of the body and AS is the surface area, into AS square into K over rho V square Cp into tau. Or HAS over rho V Cp into tau can be written as HLC by K into alpha tau over LC square. Let's say this is equation number 2. In this equation number 2, alpha is thermal diffusivity of the solids. It is measured in meter square per second and can be given as K over rho C. And LC is called as characteristics length of the body, and it can be calculated as V over AS, that is volume over surface area of the body. So from this discussion it is clear the equation T minus T infinity over Ti minus T infinity can also be written equal to exponential of HLC by K into alpha tau over LC square, where alpha is thermal diffusivity and LC is characteristics length of the solid given by volume over surface area. So many times we need to calculate this characteristics length depending upon the geometry of the body. So for some of the simple geometry which may undergo transient heat conduction process, let us calculate characteristics length. So the very first geometry is flat plate. Let us consider this is a flat plate. Let us consider this is a flat plate of length B, width h and thickness delta. So characteristics length can be calculated as follows. LC is the thing but volume by surface area. Volume will be B into H into delta, and surface area of this plate will be this one. It will have two surface area. One is of top surface, another one is of bottom surface. That is why it is written as 2 into B into H. Simplification of this will give me characteristics length for flat plate as delta by 2. So characteristics length for flat plate will be half of its thickness. Next geometry is for sphere. Let us consider a sphere of diameter capital D and radius capital R. Capital R can be written as half of the diameter. So characteristics length for the sphere will be volume of the sphere as 4 by 3 pi r cube, and its surface area will be 4 pi r square. So characteristics length for the sphere will be r by 3 or d by 6. The next geometry is for long cylinder. Now long cylinder is defined as the cylinder whose length is very large compared to its diameter. So compared to its length, its diameter or radius is negligible. So the surface area of these surfaces, top surface and bottom surface, I can neglect. So characteristics length for long cylinder can be calculated as volume by surface area. Pi r square L will be its volume and 2 pi r L will be its surface area. Yes, I am not considering surface area of top and bottom surface because diameter is negligible as compared to length. So for long cylinder, characteristics length will be r by 2 is equal to d by 4. In the similar fashion, I can calculate characteristics length for salt or solid cylinder. In case of salt or solid cylinder, its length and radius are comparable. So we are going to consider this surface area as well. So characteristics length for a solid cylinder will be its volume pi r square L over total surface area. That means this surface area plus top and bottom surface area of circular section. So 2 into pi r square is the surface area of this, and 2 pi rl is the surface area of this body. So simplification will give me characteristics length for short cylinder as r over twice of r plus l. And finally for cube of sides L, all the sides are of length capital L. So its volume will be LQ and surface area will be 6L square. So characteristics length for the cube will be L by 6. Now after calculating the characteristics length for different geometries which may undergo Newtonian heating or cooling, let us concentrate once again on this parameter HAS over rho v Cp into tau, which can also be written as HLC by K into alpha tau over LC square. And LC is characteristics length and alpha is thermal diffusivity. Can be calculated as K over rho v Cp. Now in this equation number 2, the non-dimensional parameter alpha tau over LC square is also called as the Fourier number, that is, and it is denoted by FO. So Fourier number FO is equal to alpha tau over LC square. What is its significance? Fourier number signifies the degree of penetration of heating or cooling effect through a solid. For instance, a large time would be required to obtain a significant temperature change for a small value of alpha over LC square. If the value of Fourier number is very large, that means the body will require sufficiently longer time change its temperature significantly with respect to the temperature of the surrounding. Similarly, a longer time would be required by the body to cause change in its temperature if the value of alpha over LC square is very small. So in a simple language, I can say more will be the value of Fourier number, more time will be required by the body to get affect its temperature by the temperature of the surrounding. Similarly, the non-dimensional parameter HLC by K is also called as the Biot number, and it is denoted by Bi. So Biot number Bi is equal to HLC by K. What is its significance? Biot number gives the indication of ratio of internal conductance resistance of the body to the surface convection resistance of the surrounding to which the body is exposed. So if the value of Biot number is small, it means the value of internal conductance resistance of the body will be small or negligible. And under such condition, there will be no temperature gradient existing within the body itself, or under some practical limit, the body's temperature can be assumed uniform and constant over a particular interval of time. And under such condition, if the Biot number is very small, there is no internal conductance resistance, the entire heat conduction process will be governed by the surface convective resistance of the surrounding fluid. So considering the alpha tau over LC square as Fourier number and HLC by K as Biot number, equation 1 for lumped parameter analysis can also be written as T minus T infinity over Ti minus T infinity is equal to exponential of minus Bi into F4. So this is another way of representing the lumped parameter analysis equation to find out the temperature variation of the body undergoing transient heat conduction process. Now from this discussion, we could conclude that lumped parameter analysis method is the most easiest method to find out the temperature variation of the body undergoing transient heat conduction process. But it can be questioned. There are so many assumptions involved while applying lumped parameter analysis. So one can question what is the accuracy level or what is the confidence level of estimating the temperature by lumped parameter analysis. So in order to decide the criteria to use lumped parameter analysis, we have already defined Biot number. It is nothing but HLC by K. Can also be defined as the ratio of internal conductance resistance of the body to the convective surface resistance of the fluid. Please correct this. Please read it surrounding in place of body. Convective surface resistance of the surrounding. So what does it mean? Lumped system analysis will be exact when Biot number is 0. That is when conductance resistance of the body is almost 0. But this is not possible in many cases. This Biot number must be 0 is the ideal condition. So the most accepted practical condition for using lumped system analysis is if Biot number value is less than or equal to 0.1, we can confidently and satisfactorily use lumped parameter analysis to find out the variation of the temperature with respect to surrounding. And if you are using Biot number is less than or equal to 0.1 for any system, any such lumped system, under this condition, the error associated with this estimation will be less than 5%, which is quite low. So the criteria to use lumped parameter analysis is Biot number must be less than or equal to 0.1. And we can use satisfactorily with the errors less than 5%. So with this, I come to an end of this video lecture. After watching this video, you will be able to discuss and explain various aspects of lumped parameter analysis, able to define thermal time constant and its importance, able to define Fourier and Biot numbers and their significance in transient heat transfer process, and will be able to apply lumped parameter analysis based on its selection criteria. So thank you for your passionate listening and happy learning.